So what we've done so far is we've applied valence bond theory to species that contain single bonds only. Well, we also know there are triple and double bonds out there. So in single bonds, so we're going to focus on those. Let's talk first about double bonds. Now, double bonds, for example, like you see in ethene here, each of those carbons has a trigonal planar geometry. And what we know is that any atom with a trigonal planar electron geometry is going to be sp2 hybridized. So we acknowledge and can identify things that are trigonal planar, and then we immediately know those are sp2 hybridized. Now, let's talk a little bit about what this means. When something is sp2 hybridized, it's going to have one unhybridized p orbital and then 3 sp2 hybrid orbitals. So this, what we're going to see here is that, and you'll see it on the next slide, is that the sp2 hybrid orbitals point to the corners of a triangle, right? Because when we think about this, right, we have this, it's kind of like a triangle because we have about a 120 degree bond angle. And then the unhybridized p orbital is perpendicular to that triangle. So because sp2 hybrid orbitals are generated by mixing one s orbital and two p orbitals, each sp2 orbital has 33.33% s character and 66.67% p character. So what we find here is that we have more s character than what we would see in an sp3 hybridized orbital. So let's visualize this, looking again at some of these orbital diagrams. So here's an unhybridized carbon. This is something we're used to. And then here is the sp2 hybridization. So what we're going to notice is the sp2 hybridization is lower in energy than the 2p orbital here. And so we also see here are the triangles that we were talking about, right? And how if we've got that 120 and we've got the corner of the triangles, then this is perpendicular to that. Now, we're going to look at this in another way. So this is figure, we just saw figure 311, right? When we look at that unhybridized p orbital, so if we see the plane here, here's our sp2, and then here is that p, because remember they all overlap over the nucleus here. And so this gives us a visualization. So now that we know the valence orbitals that contribute to each carbon in ethene, let's construct the molecule's valence bond picture. Okay, so here are our two carbons that are sp2 hybridized. Here are those flat in purple sp2 hybridized orbitals, and here are the ones that are flat in purple as well that are sp2. The ones here in blue are the unhybridized p orbitals, and then of course we have our sigma bonds with our hydrogens here. Okay, it's this overlap here that is a sigma overlap. Now, that is just one of the bonds. We also have a double bond here. Well, what we're going to find is that double bond, what we're also going to find is that these p orbitals can somewhat overlap and form a pi bond. So the p orbitals here, right, and they're showing you the overlap here with these kind of arrows to show that these overlap, and then they kind of branch out here to form this double bond. Now, I want you to notice the double bond here is farther out from the nucleus. That makes it more reactive. So even though this overlap is not immediately noticeable, the p orbitals do overlap, and they overlap on opposite sides of the carbon-carbon bonding axis. So they're on opposite sides. A pair of electrons occupy an orbital with p symmetry is called a pi bond. Now, in summary here, that means that any double bond consists of one sigma bond and one pi bond every time. You see a double bond? It's got one sigma bond, from the overlap of the sp2. That comes from the sp2 overlap, and then 1 pi bond, and that comes from the p orbital overlaps. And so that's what we see. Now, sometimes you can have trigonal planar geometry in single bonds. For example, if you have a carbon that has 3 sigma bonds here, with no lone pairs, so it's got this plus charge, it's going to have a trigonal planar geometry as well. And that means it's sp2 hybridized as well. And so with this in mind, we can draw the valence bond picture of a carbocation like Ch03 which we see here, where we just have a sigma bond, and then these p orbitals here are empty, so they're not going to bond or form a pi bond with the sp3 orbitals here. Okay, so those are some things to kind of keep into, or kind of think about as we look at carbocations, right? Well, let's talk about triple bonds now. We've talked about sp3 hybridization to describe atoms with tetrahedral electron geometry, and sp2 hybridization to describe atoms with trigonal planar geometry. Now we can turn to atoms with this linear electron geometry. Okay, so things with triple bonds. We're showing acetylene here, which has the carbon-carbon triple bond there. And anything that's linear is sp2 hybridized. A few things about, I said sp2 hybridized, it's sp hybridized. A few things to note here about sp hybridization is it contributes 2 sp hybrid orbitals and 2 unhybridized p orbitals from the valence shell. The hybrid orbitals point 180 degrees apart along the same line. You have 2 unhybridized p orbitals that are perpendicular. So those p orbitals are going to be kind of perpendicular right in here to the sp orbitals and are perpendicular to each other. Now, because the sp orbitals are generated by mixing one s and one p orbital, each sp has 50% s character and 50% p character. That was cut off there. Okay. Now, let's visualize this hybridization. And so here's our normal unhybridized carbon. When we come over here and look, we see here are our 2 hybrid molecules. They're linear here along the axis. And then here are our p orbitals. One is going to be right aligned here on the x-axis, and the other is going to be aligned on the z-axis here. So they're perpendicular to each other, and then also perpendicular to the x-axis there. And so you can have different orientations. You can have, of course, where the sp is along the x, where the sp is along the y, and then where the sp is along the z. So we still see these different orientations when we have a sp hybridized orbital. So what does this mean for us? We have 2 p orbitals now that can overlap. And so we see these p orbitals here. They can overlap to form a pi bond. And then we have these hybrid orbitals that overlap to form a sigma bond. This means for us, any triple bond consists of 1 sigma bond and 2 pi bonds. Okay. So we see 1 sigma bond here and 2 pi bonds. And again, you'll notice those pi bonds are farther out than the sigma bonds, and so that makes it very, very reactive. So here's our strategies for success. My suggestion is to memorize this. This is what we're going to use most often in organic chemistry. These are our 3 electron geometries that are going to come up over and over and over again. I want you to look at some of the things here. 2 electron groups, linear. Its hybridization is sp, right? Number of electron, and the bond equals 180. Number of electron groups 3, trigonal planar sp2, right? And it's 120. 4, tetrahedral sp3, 109.5. This is just really, really helpful for us. So let's look at what a problem would look like. So it says what's the hybridization of each non-hydrogen atom in this molecule, and how many total sigma and pi bonds are there? So here are some questions to ask yourself. What's the electron geometry of each non-hydrogen atom, and what hybridization is associated with that geometry? To answer questions about electron geometry, it really helps us to draw all the carbon-hydrogen bonds in this molecule, because that's going to help you identify the electron geometry. So if we kind of redraw this molecule, we have a carbon here with a double bond. That means it's going to have one hydrogen. Carbon here, it's going to have one hydrogen. Single bond, carbon. This carbon's going to have two hydrogens. We're going to go up here to the oxygen. I'm going to go ahead and draw on these electrons too, because that's helpful. Okay, there's a carbon. It's got 3 bonds, so it's going to have one hydrogen. It goes to a carbon, 1, 2, 3, and then a nitrogen with a lone pair of electrons. At least at the beginning, it's a lot easier to identify the electron geometry if you can see the carbon-hydrogen bonds and the lone pairs here. And so knowing those electron groups surrounding each atom, we can then determine the electron geometry. So for example, this carbon right here, it's electron geometry, right? It has 4 bonds. It's going to be tetrahedral. And so once we know the electron geometry, we can figure out the hybridization. Anything that's tetrahedral is sp3. Okay, we're going to come here to this next carbon. We see it has 3 electron groups off of it, so we know that's going to be trigonal planar. And so anything that's trigonal planar is sp2. Same thing with this carbon here. This one is another tetrahedral. So it's going to be sp3. This carbon is another trigonal planar. So it's going to be, oh, I may have lied there. Nope, that's tetrahedral. Well, let's just back that up, because there are 4. So it's going to be sp3. When we look at this oxygen, it has 4 electron groups, so it's also going to be tetrahedral, which is sp3. We look here, this sucker's linear, that carbon, so it's going to be sp. And then when we look here at this nitrogen, what we find is it's also linear, and so it is also going to have, maybe, an sp electron geometry. So we've pretty quickly identified the hybridization of the non-hydrogen atoms here based on the fact that we know and can identify really quickly things that are tetrahedral, trigonal planar, and linear, and then know that tetrahedral is sp3 hybridized, trigonal planar is sp2, and linear is sp. Now, it asks here, how many sigma and pi bonds are there? So we've solved this above, but now it says, okay, what type of sigma and pi bonds? So here's the deal. The question that it asks you is what types of bonds make up single, double, and triple bonds, and how many single, double, and triple bonds are there in the molecule? We know when we do this that there are, when we go through here and count, right? So if I go through here and count, I'm just going to count, well, maybe if I can make this bigger, let's see. I'm going to pause it for just a second. All right, so I've grouped it, now it's bigger. So let's look at this just really briefly, and I want us to count the number of sigma bonds. And I think we're going to try to, I think I'm going to highlight them, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 single bonds, okay, and they're highlighted in green. And we know that single bonds are sigma bonds. So we know from just the single bonds, we have 13 sigma bonds. Now, next we need to look to see if we have any double bonds. We don't have any double bonds, but we do have a double bond. So we're going to highlight that double bond there in blue. Right? So we find that double bond, we know we have one double bond. And in that double bond, we know we're going to have one sigma and one pi bond. And then we also have a triple bond, which we're going to highlight right here in yellow. And we know from that we have one triple bond. And a triple bond gives us one sigma and two pi bonds. So in this molecule, what we find, we're going to add up all our sigma bonds. We find that there are 15 sigma bonds and then 3 pi bonds. Okay? And so this is just a really quick way for us to be able to identify each of these individual things. Now, this concludes Screencast 2. I accidentally brought over a slide from Screencast 3, so even though it says there's another slide, there's not really one. And so we are going to pick up here in bond rotations about single and double bonds in the next Screencast.